Good afternoon, NASA interns, scientists, and the rest of the audience. My name is Shaurya Pathania, and my team members are.
Brooklyn, McGough.
Christine Choi.
Today, we will be discussing the research we have taken part in over the past few weeks, named Race Against Climate Change, a case study of vegetation in New York and Atlanta. Here is what we will be discussing throughout our presentation, highlighting the many parts of the scientific process we have gone through. So let's start with the introduction. Urbanization is a common phenomenon in America now, with it happening across the nation. It started in the 1950s and has grown exponentially since then. However, when urbanizing cities, the environment has been put on the back burner, normalizing unsustainable practices in nature. This unsustainability has led to the exacerbation of one big issue, climate change. We will be focusing on two symptoms, CO2 production and the urban heat island effect, which is the increasing or warming of temperatures due to large amounts of heat reflection and emission from man-made buildings. And this is where we land on space data. Satellites and space instruments are unique in their data that they can give us because they provide us unique insights that cannot be found anywhere else in the world. Like the satellites and instruments on the page listed here, like the ISAT-2, JEDI mission, MODIS Terra, and the OCO2, we were able to analyze and look at the data to find ways to combat climate change and have a greener future.
Methods. First, for locations. We chose New York City's Central Park as a control for the study due to their stable tree population and compared that to Greater Manhattan, along with downtown, suburban, and rural areas of Atlanta due to their varying levels of tree height, biomass extent, and urbanization. As for a time frame, all data was collected from 2018 to 2020, coinciding with ISAT-2's initial launch in 2018 and the onset of the COVID-19 pandemic in 2020. OCO2 extraction. Using QGIS, a spatial software tool, we outlined a shape around each location. With each point on the shape came a coordinate. We programmed a Python function that calculated the spherical average coordinate pair of all the coordinate points in each shape. We used a spherical average because that took into account the Earth's curvature, whereas a centroid average assumed that the Earth was flat. We then used the spherical average coordinate pairs to find carbon dioxide data from the OCO2 satellite through Earth data. Since the data was presented in a netCDF4 files, which aren't readable in QGIS, we programmed a Python function that converted netCDF4 files into CSV files that were readable in QGIS.
Above ground biomass density extraction. We extracted the above ground biomass density from the JEDI mission located in NASA's Earth data software. We then processed and visualized it using the QGIS software. In QGIS, we used polygons that were digitized manually to extract the density values using the zonal statistics plugin applied to the raster dataset. This same method and application was used to do land surface temperature extraction.
Next, we went onto the canopy height data using the ISAT-2 satellite. We first went onto Open Altimetry, a software created by NASA specifically for the visualization of ISAT-2 datasets. Using the software, we specifically selected the ATL-08 laser on the ISAT-2 satellite, which is the only instrument on the satellite that collects vegetation height data. Using the calculated locations and time spans from earlier, we found the data we needed. Additionally, we developed equations to calculate deforestation rates and percent change in biomass density using the canopy height from the satellite.
As previously mentioned by Shaurya, ISAT-2's canopy height data was used to calculate the biomass density percent change, as the JEDI instrument only provided biomass density for 2020. Next, using such derived equations for carbon sequestration, we programmed a Python function to calculate Atlanta's carbon sequestration. Satellite results.
Atlanta's biomass. Seen in Figure 1, Atlanta's boundary is overlaid on an above-ground biomass density map. Figure 1.2 shows the pixel visualization of downtown Atlanta with a mean density of 15.71, while Figure 3, much lighter, shows Atlanta's rural area, which is a mean density of 130.71. And to the right of me, Figure 1.4 shows suburban Atlanta with a mean density of 52.66, just in the middle of both. When we compare this to Central Park, you can see on the left there's a pixel visualization of Central Park's mean density of 43.29. This biomass statistic suggests a managed urban park with a moderate number of trees, shown in the standard deviation that was extracted, with fewer trees and less variation than compared to the much larger and grander rural Atlanta. The the land surface temperature means. Downtown Atlanta, although high, has 315.12 Kelvin, while rural Atlanta is much cooler with a recorded 313.82 Kelvin. Suburban Atlanta is much higher with 317.95 Kelvin. And when we're looking at the New York regions, we have Central Park with this 316.22 Kelvin, and the Greater Manhattan, just located souther with the boundary, is 316.44 Kelvin.
Carbon dioxide content in Atlanta. The highest average carbon dioxide content in parts per million for Atlanta is in downtown Atlanta. The middle average content is in suburban Atlanta, and the lowest average content is in rural Atlanta. Downtown Atlanta also has the greatest carbon dioxide content growth rate, with suburban Atlanta following and rural Atlanta the least. On the graph, you can see a slight dip in all three lines in carbon dioxide content around October 2019. We assume this discrepancy was due to Atlanta students partaking in the 2019 global climate strike in September. Carbon sequestration in Atlanta. Downtown Atlanta has the most drastic carbon sequestration change rate out of all three locations, at a decrease of 49% sequestration annually. Next, suburban Atlanta has a negative 27% sequestration rate annually. And finally, rural Atlanta in fact increases slightly by 2% annually. Overall, rural Atlanta was the only location out of all three locations in Atlanta that had increasing carbon sequestration.
Canopy Heights provided us with a lot of insights as well. First, we were able to find the deforestation rates in all three locations of Atlanta, being 50% for downtown Atlanta, 28% for suburban Atlanta, and then negative 9% for rural Atlanta. This means that rural Atlanta did not experience deforestation, but the other two locations did, and that overall less trees exist the more urbanized Atlanta gets. Additionally, with the data and the equations we developed previously, we found that the percent change of biomass density is 2% for trees in Atlanta.
Correlations.
How biomass affects surface temperature. The calculated correlation coefficient is approximately negative 0.411, which suggests that the above ground biomass density and temperature given has a negative correlation in relation, but as above ground biomass increases, temperature slightly decreases. And you can see this in rural Atlanta with the AGB and temperature.
How biomass affects carbon dioxide and carbon sequestration. Overall, in Atlanta, increases in biomass produces increased carbon sequestration. Additionally, overall in Atlanta, as carbon sequestration increases, the amount of atmospheric carbon dioxide content parts per million decreases. All three values, carbon dioxide, sequestration, and biomass density for rural Atlanta are relatively unchanged with only a slight increase over time.
Green spaces could be our future. The effects of implementing green spaces in New York City is seen on the graph above. The Central Park zone, which is Central Park and 3 blocks out, has a recorded land surface temperature of 316.22 Kelvin, while the Greater Manhattan region, located a little south, is 316.43 Kelvin.
Finally, the conclusion. First, our broad hypothesis is supported that vegetation cover in urban areas are effective at mitigating the effects of climate change. Based on our examinations of CO2 production and the urban island effect, we were able to find support that vegetation is able to reduce the amount of CO2 in our atmosphere as well as lower temperatures. This means locations like New York City can be used as a blueprint for green infrastructure for locations like Atlanta, which need it. Also, space data is very useful for combating climate change and should be studied and used more in future research to help create better functions to prevent climate change in the future.
The NASA SEES program has definitely helped me as an aspiring architect, offering multiple benefits that both enhance the design process and the final outcomes of my future projects. Mapping what I learned provides vital spatial data that informs site analysis, allowing me to understand the topography and existing architecture that can be used in the future.
For me, the NASA SEES program has provided me with invaluable skills and insights essential for my aspirations as a computer scientist focused on the environmental field. Through hands-on experience with various software tools, data analysis, and coding, I learned how to manipulate and interpret complex environmental data and how to leverage data-driven approaches to promote sustainability.
For me, the NASA SEES program was an incredible experience and provided me with a lot of data and learning about how to analyze data over a wide range of topics. Additionally, with the experience I gained using many online software tools as well as data analysis tools, I was able to learn a lot and gain a lot of experience for what I can use in the future as an aspiring data scientist.
Just some highlights. Some of our highlights was the iFly experience, the Z-Cube, the main event, and Dave & Buster's, while some of our challenges included the accessibility of some data types, project planning, and deriving equations for carbon sequestration.
So finally, we would like to thank our mentor, Dr. Simurda, for all the help she has given us over the past few weeks to complete our project, as well as the NASA Space Program as a whole. With our presentation coming to an end, does anyone have any questions?